let's look at all of the things that can affect our pressure. So the pressure is the amount of times a particle impacts our wall. Okay, so this is effectively the number of impacts. Okay, so what things are going to affect that pressure? Well, how about temperature? What happens if I increase the temperature? Does that increase the number of impacts? Well, if I increase temperature, I increase kinetic energy, I increase motion. Well, the more things move, the more likely they will impact the wall. So yes, an increase in temperature is directly proportional to an increase in pressure. Okay? How about our volume? What happens if I increase the volume? How is that related to our pressure? Okay, so let's think about our container. If we had a small container, now make that container larger. Don't change anything else about the particles. Okay, so you're not adding more particles in, you're not taking particles out, you're not changing the temperature. Okay, all we're doing is changing the size of the container. What's going to happen to the pressure? Okay, and for those of you being like, well, when I blow a balloon in, it gets bigger. You're blowing particles in. That's going to be the next question. This is just volume and pressure. Okay, if I have that balloon, but now I make it bigger, okay, and stretch that out from the outside, what happens to the number of impacts on the sides of that balloon? They'll actually decrease. We've given more area, okay? And so this is best done by hand drawing visually, right? We get 4 particles in that box. If I now make that box larger, what happens to the space between those? They get much larger as well, which then means I impact the walls less frequently. So as I increase the volume, the pressure actually decreases. So this is an interesting relationship. We're getting an inverse relationship between volume and pressure. Whereas with temperature, it was a direct relationship between temperature and pressure. And I'm sure there's a better word than direct, but that's all I've got. Okay. The last one, as we started to allude to, what happens if I add more particles to that container? Notice now in this situation, I'm not changing the volume. It's the same size box. So if I increase the number of particles, and God, I wish there was a shorter way to write out the number of particles. Hold that thought. How is that going to relate to the pressure? Well, the pressure will also increase. More particles means more times the sides of that container are going to be hit, so we get a direct relationship here. Okay, between, and I'm not going to write numbers of particles again. It'd be nice if I had an analogy for this. Well, numbers of particles in chemistry we could reference as moles, which means we could write M, except M is meters. So meters was already taken. We can't use that one. Well, I could use capital M, but that was molarity. So molarity was already taken. Well, dang, what could I use? Well, let's go up to where it was originally sourced. Number of particles is what we're referencing. When we're talking about our moles or our number of particles in gases, it's N is our symbol. So a direct relationship between moles and pressure. One thing you might start to then ask, once you've got all of these relationships, is we know that there's relationships between moles and pressure and volume and pressure. So shouldn't there be a relationship between moles and volume? Yeah, there is. Shouldn't there be a relationship between temperature and volume? Yes. Good job. Isn't there also a relationship between temperature and moles? Yes. All of these things are now interrelated through that pressure concept. Okay? And so depending on the person studying these individual relationships, they made these observations and they got to attach their name to them. So we get Boyle's law and Charles' law and Gay-Lussac's law, or Guy-Lussac, however you want to do it. We get Avogadro's law. There are all sorts of laws that come out of this, which is a bit silly because all they're trying to do is establish those relationships. And really, none of them does a good job of actually tying all of those pieces together. Okay? And eventually that's what happens. Someone went through and said, well, hold up. What if I take all of those things and I put them all neatly into one giant, instead of approximate or comparison, what if I put them into a single relationship? And it turns out that we can do that. We can say PV over NT. Notice these are all of our variables: pressure, volume, moles, and temperature. And when I put them together in this fashion, they will equal a constant. And that's kind of neat. Okay? Don't worry about what that constant is yet, but let's make sure these relationships can come out. Okay? So what we're saying is that all of those things equal some number. Okay? Okay, and because I feel like it, we're gonna make it a pineapple. Okay, so we're looking at pineapples. We said pressure was directly related to moles. So if I increased the pressure, what did I have to do to moles? Well, I also had to increase the moles. Okay. Well, if this equality was true, that would have to be the case, because pineapple doesn't change. It's always pineapple. It's always constant. So if the pressure goes up by twofold, twice the pressure, the moles must go up by twice. Okay, that's kind of neat. Okay, so this relationship, believe it or not, does all of our pieces. Okay, we talked about moles and pressure. How about pressure and volume? We said those were inversely related. Well, if the moles and temperature don't have an effect on this because they're not changing, if the pressure goes up, the volume must go down, inversely related, so that this equality still equals pineapples. So all of those relationships come out of this, and that is really phenomenally cool that someone was able to put all this together to make these observations. Cooler yet is that we have experiments to show that this is actually valid, and that's fascinating. And you can do those things with different pressure sensors and syringes and all sorts of fun jazz like that, but we aren't. And we'll just say we aren't because we're stuck at home listening to this stupid lecture. So, what is that R? It's a constant value. The exact value for that R is 0.0821 with a very complex unit afterwards. Atmospheres, liters, moles, and kelvins. Why would it be so complex? Okay, well, R is this equality, right? Well, what were the units of pressure? Atmospheres. What are the units for volume of a gas? Liters. What are the units for moles? Well, moles. That was a bit of a dumb question. And the unit for temperature is going to come in as Kelvin. How do you know it was Kelvin and not, say, degrees Celsius? When we say the units were for R, that's where the units are coming from. Why do we do it as Kelvin and not degrees Celsius or degrees Fahrenheit? Well, what happens if we use degrees Celsius? Is there something colder than 0? Yes, which means the temperature value we would enter into this expression would be negative. That throws a massive monkey wrench in this equality, and it actually entirely shuts it down. Okay? So what we have to use for this is the Kelvin scale, because the Kelvin scale is not negative. Okay? We don't have negative kelvins. Okay? And that's why we end up using Kelvin. That's why we needed Kelvin, because Kelvin as a temperature scale allows this expression to become true and useful. And that's kind of neat. Okay? So, what do we do with this? Well, this is now a formula. For all those people that have been dying to have a formula so that you can plug and chug, ta-da! Here it is. You can now plug and chug to your heart's delight. It might be confusing to go through and memorize it as this expression. So typically people will memorize it as PVNRT. Okay? Why that particular spacing? Because that's how I was trained in high school. And in high school, I was trained this because this could kind of become a pseudo name, and we get PivNert. For those of you that didn't hear that, let me try that again. PivNert. Yes, that sounds stupid. But if it helps you remember, the sequence in these, all the better. Okay, this also gets rid of the fractions, so we don't have to worry about doing any kind of divisions, but it does mean in this expression written as pivnert that we do have to realize that if we wanted to solve for volume, we would need nRT over P, and so we would have to do some of the algebra to go through and do that solve. Okay, but that's what's cool about this is I can rearrange that expression to solve for any one of those 4 variables as long as I have the other 3, and that's neat. Okay. The other thing that's super, super powerful here, we're actually going to see here on the next slide, because these are now just saying we're going to rearrange. So these are just rearrangements to solve for either pressure or volume, but we could rearrange it for moles or for temperature. Where this becomes incredibly useful is that I know that if I take a particular gas and I change one of those variables, the R, the constant, is still always the same, which means I can get a neato expression. Okay, and I had to advance that so we could get to the bottom of that. What is that neato expression I can get? I know since these things are both equal to R, that pressure at conditions B, volume B, NB, and TB, these 2 things, I could set equal to each other. Why has that become useful? I can now potentially solve for a missing or a changing variable. Okay, and that's what this question down below is saying. The volume of a container is doubled. Assume the temperature and moles are not changed. What happens to the pressure? Okay, so what we've got is a container. We'll call this conditions A, and we doubled the volume. So the container B gets bigger. Okay, what happened to the pressure? Okay, so one of the things some of you might be able to do is to reason through exactly what happened, because we talked about some of this. Because the moles are all the same, we would expect the pressure to go down because our volume went up. Okay, so that's cool. We know an approximate, I want more than that. Because what your answer choices will be, the volume doubled, the volume halved, the volume quadrupled, the volume quartered. Okay, so we need a little bit more specifics behind it just decreasing. So how do we go through and do that? Okay, well, again, I'm going to give you a second here, largely because I need to go to the bathroom, to attempt to put this down. Okay, in just a few seconds, what I'll do is summarize the pieces of information found within the text. So to simplify all of the work or the algebra behind this, I'm going to go through, instead of being referencing as PA and PB, A is the blue color and B is the red color, and this is why I've drawn it this way. Okay, so what we can now go through and do is start to make our substitutions into the expressions shown above. Okay, so PB, okay, well, that's what I'm solving for, so I'm going to leave that one alone. Okay, VB, well, what is the volume of the red container? Well, it's twice the volume of A, so times 2VA. So these are all times in here. The moles of B, well, that would just be the moles of A. And the moles, or the temperature of B, would just be the temperature of A. Okay? So now what I can go through and do is complete out this equality. This was PV over NT. And hopefully what you notice is that our moles are the same on both sides of the equation. So I can multiply both sides by N, and those would cancel algebraically. The temperature would also do the same thing, and the pressure, or not the pressure, the volume would also do the same thing. Okay? And so what that expression now swiftly turns into is P times 2 equals P. Okay, where red P and blue P. What was I being asked to solve for? I wanted to know the pressure at the second conditions, PB. So right now I'm not there yet. So what I would do is divide both sides by 2, and I would get that my new pressure should be 1/2 my starting pressure. Holy monkeys, I've now actually quantified how much the pressure decreased based off of using the ideal gas law. Okay, that's the point of that. That's why this is kind of neat. Okay, so with that, what we're going to do is move into the next little topic, which is super exciting for me. How many moles of neon gas occupy 2.34 liters at STP? So we just walked you through all of this fun stuff. So you should be able to go through and note that at standard temperature and pressure, we have a temperature of 273 Kelvin because we're at 0 degrees Celsius, so it's 273, a pressure of 1 atmosphere, and we could now go through and solve into our ideal gas equation. Okay, so what I'm about to launch into is that solve, but I'm going to let it run, and during the video running, I want you, in that tiny little space above, to go through and solve this too. We are solving for the moles of neon, given that you are starting with 2.34 liters, okay, of neon. And you should be able to do some calculations out here, okay, just kind of helping you out, giving you a step, okay? And so with that, I'm going to launch into our PV equals nRT. So PV equals nRT. So this is one of those things where you might be selective and stop listening to me. That's okay. I want to solve for moles. Well, moles was that N, so I want N equals PV over RT. Okay, and now I could start to actually go through and sub stuff in here. The pressure was 1.00 atmospheres. Okay, and I'm going to do a little bit of kind of fancy footwork here, and I'm going to decide that I'm just going to do the R, which I always forget that, so hopefully I got it right here. Liters times atmospheres over moles times kelvins. And then our temperature of 273 Kelvin. And here's the little weird kind of fancy footwork I'm going to do. And then I'm going to multiply that by the volume. So I'm going to keep the volume kind of separated away from this. Okay, so let's separate that volume out. The volume should be in the numerator. What did we say it was? 2.34. And, you know, just for giggles, 2.34 liters of neon. And we'll put a 1 there. Okay. And since I've got it set up, I'm going to go through and now enter this all into the calculator. And by all of it, I'm just going to do some of it. 1 divided by 0.0821. It might be nice if I entered into the calculator, right? 82211. See, this is why I don't enter things into the calculator live streaming, because I screw it up so badly. Okay, and I, in theory, get, assuming I did this right, let's look at it. It's 0.004461009. That's probably a bit excessive, but always got to prove a point, right? 4. If we look at the units there, the atmospheres cancel, the kelvins cancel, our liters will cancel. So at the end of this, my units are going to look a little bit weird. It's going to be 1 over moles. Okay, and then times our 2.34, because I got rid of that unit, so that unit's not there, times 2.34. And let's see, did I actually do my calculation right? That would be embarrassing, wouldn't it? Well, we'll find out here in a second, won't we? I come up with the number 0.104. I mean, we can keep running numbers out there for a little bit. And then moles. How did the moles go up? Okay. This becomes some kind of math footwork. 1 divided by 1 over 2 is actually equal to 2. I'm doing the same thing here. We're just flipping the moles out on top of this. And I'm a little bit nervous that I goofed that calculation, so I'm going to keep talking, hopefully giving you enough time that you could go through and solve this. Of course, we gotta... Okay, cool. It looks like I'm good, and I think I got the answer. Hopefully, you also already got the answer, and hopefully, you got it a hell of a lot faster than I did. Because hopefully you did none of the work that I showed. Okay? Because you were intelligent and you went, but this was at STP. And if I remember correctly, if I am at STP, liters and moles is a conversion factor that exists, and it's 22.4 liters. It's 1 mole. And now if I go through and do my calculation, the liters cancel and I would get moles. And the number that my calculator spits out when I decide to do it in that fashion comes out to be 1045. But pretty dang close to the same. So who's right? Because really, I'm hoping that what you guys did was this up there, okay? And I'm going to say you cheated, and that the way I did it was the real way to do it, okay? What's going on? Who's right? Because we both ended at the same answer. Does that mean we just randomly punched things into the calculator correctly and locked into it? No, okay? That thing that you were told to memorize, 1 over 22.4, if you enter that into the calculator, 1 divided by 22.4 gets you exactly that numerical value. That conversion factor that you are told to memorize is a direct result of the ideal gas law. And all that someone has gone through and done is simplified the calculation by picking an effectively arbitrary temperature and pressure so that they can give you numbers to memorize. Okay? So both work for the sake of this class as long as we are at STP. But if you aren't at STP, then you should be launching into the painful aspects of PV equals nRT. Okay? The majority of the time you will be at STP because that's what we've expected you to memorize. The textbook throws a bunch of questions at you at 1 mole is 22.4 liters and expects you to go through and just memorize and use that. There is some utility to it at STP. The full, long, painful science of it is the ideal gas law. It is PV equals nRT. That's where those relationships are coming from, and that's what you should be using. I am not going to force you to use that, though. Okay? So what do I want out of this? Your responsibility, as much as it pains me to say, is 22.4 liters of a gas is equal to 1 mole of a gas at STP. So if you can memorize that, you are good to use it. After that, I would like you to recognize the utility of PV equals nRT. Okay? That is up to you how far into PV equals nRT you want to go. But I do expect you to realize that there is a relationship between volume and temperature, volume and pressure, pressure and moles, pressure and temperature, moles and volume. Okay? All of those relationships exist, and you are responsible for all of those relationships. If you choose to memorize those as each individuals, then you are good to do so. If you instead choose to memorize PV equals nRT and understand the algebra that allows you to interpret each of those individuals, all the more power to you. I will not ask you to solve PV equals nRT. Okay? I will ask you to solve aspects of it through simple kind of relationship stuff. Okay? Which I know is a challenging line to walk. And if you are not in my lecture, for whatever reason you're watching this, you need to make sure you understand the expectations of your individual instructor. Okay? I personally, for this class, don't see the need to go all the way into solving PV equals nRT. Okay? Hopefully we'll let that sink in, and we'll move on to our next, I think, 2 slides. Dalton's law of partial pressures. Okay, a lot of this kind of stems from ideal gas. Really, all Dalton's law says is that if you want to find out the total gas pressure in an individual container, figure out the pressures of each of the individual gases. When you add all of them up, that's the total pressure. Okay? Remember, in ideal gas, no particle has a different volume, which means all particles are occupying the exact space, same space, which means they're effectively distributing the same pressure. So if I just know the pressure of, know how many atoms, regardless of what they belong to, okay, the total pressure is the sum of all of those components. Okay? But if I'm now making a balloon, say, and I want 50 parts hydrogen and 20 parts oxygen and 30 parts nitrogen, okay, the total pressure is then going to be the pressure of all of those. Okay? So if we take a look at a sample of noble gases, we'll address why noble gases here in a second, and we look at those individual pressures. If I want to know the total pressure of the entire sample, I just add all those numbers up. That's it. Like that's all you have to do. What if I know the total pressure, but I don't know one of the other substances? Well, now I do the algebra to solve for that missing substance. Okay? I'm not going to do any math solves there. You can talk to me or look for examples in the textbook to push on that. I will ask this question about the noble gas. Why would I have picked noble gases for this question as opposed to any other gas? Okay, well, the noble gases don't react with each other, so the noble gases of all our gases are the most ideal because they don't react, period. And because they don't react, that makes them a little bit more ideal. Whereas oxygen is a very reactive gas, and so if I was to look at an experiment with oxygen, it's probably going to deviate from the ideal gas law because oxygen is so reactive, that there are attractions between it and other things. Okay? So for the sake of this question, noble gases was picked to really emphasize that ideal gas relationship. We kind of addressed this a little bit, kind of not. For our Kelvin scale, we needed it to help us explain PV equals nRT. And with that, we now have an absolute scale, which is pretty awesome, that we know ends at a 0 point. And yeah, we now have an absolute 0. We don't go to negative temperatures, and that's kind of neat. Okay? So at absolute 0, we have no energy and all stuff should stop. Right? What stuff? All stuff. No motion, no energy, period, bar none, done. Okay? That sounds pretty crazy to think about because electrons are constantly moving all over the place. How could we ever have a system where we had an absolute 0 where there was no motion? Exactly, that's what makes it interesting. Okay? So that's all absolute 0 is. It's our theoretical limit. Okay? Why theoretical? Because if everything stopped, how would we measure that it had stopped? I think we run into a Heisenberg issue there, though I've been told that's not true. I'm not quite sure I believe it, but I've been told that by people much smarter than I am, which really isn't all that hard. So we get an absolute 0. Kelvin equals 0 is as low as we get. And with that, we have now covered the entirety of Chapter 10 in probably one of the longest videos. I do apologize for that, but we're at least done